I have actually something that Cheryl gave me, but I'll just invent an introduction here. So Ben Jang John's been at HAO off and on for many years. First as a grad student via the ASP visitor program, then as an ASP postdoc. Then I think for a short while you were even a project scientist at HAO. And then he interviewed for a faculty position at the University of Hong Kong, and decided to go there after the time that he spent at HAO. And over this period, when he was a graduate student at Dartmouth College, he did a number of things, studied the impacts of electron precipitation, galvanic Poynting flux, ionospheric outflows on the geospace system, and I would say made some pretty amazing discoveries and provided insights into those phenomena. And then after that, co-developed the Gamera simulation code, which is now being used by the Center for Geomagnetic Storms and also by quite a few people at the University of Hong Kong. Upon leaving the United States, Ben also traveled to the outer planets. He left geospace and has been working mainly on the Jovian magnetosphere, but not exclusively. And that's what he's going to tell us about today.
All right. Thank you very much. So I think even though I'm working on mostly the giant planet magnetospheres, but the physics is the same, right? So that's still the same thing. So one thing to mention is that we just changed from Earth Science to Earth and Planetary Sciences department. So now I'm in the officially planetary science group, although the focus is Martian geology, although we don't know what we're going to do with that. And also this is mostly summary work of excellent graduate students, which means that I'm getting more and more useless just to try to present other people's work. And also collaborators, my colleague Zhonghua and Peter from Alaska and JJ. And also the theory I'm going to show, it was inspired by Bill's paper he didn't even remember. And the question came from a talk I gave at a mock conference last year, given by Fran. And she questioned me about this. I had thought about this very carefully, so I did a lot of work trying to answer this question, which is a question that we don't know, is that whether the Jovian magnetosphere is interchange stable or unstable because it rotates really fast. So a quick summary of the magnetospheres, and you can see that the magnetized planetary magnetospheres are more or less similar. Jupiter's giant, Saturn's smaller, Earth, Mercury, they're getting smaller and smaller with a dipole field squeezed on day side, stretched at the night side called the magnetotail. And if you look at the aurora, they're more or less similar, like you have aurora on Earth, on Saturn, and also Jupiter. Jupiter is slightly different, you not have an aurora over, but you also have the polar images over there. So the whole polar cap is bright in the Jupiter problem. That's related to the structure of the magnetosphere. So if you look into the dynamics of the magnetosphere, this one is the Earth magnetosphere. That's a movie made by John Lang a long time ago, showing you the boundary cage and the bursty bulk flows, the field, solar wind coming from this side. So it's mostly driven by the solar wind. That's what the terrestrial magnetosphere looks like. But for the Jupiter problem, it's quite different because this is the one that you see. You see the plasma density in the equatorial plane and the field line currents, or the field curvature in the XZ plane. And also the color shows these structures, finger-like structures, they're rotating. They're actually interchange structures. And these are the locations of the moon. So if we send spacecraft over there, these structures should be verified by the future missions, and that's what happened. So you can see that when it rotates, everything's much more different, especially the polar region with lots of energy and flows. So that also gives you the aurora. So one of the biggest findings that we did with the Gamera calculations, that this is actually from the MFL. So you should see that the topology of the magnetic field is very different from the Jovian magnetosphere. So solar wind comes from that way. The green lines connect to the INF, interplanetary magnetic field. So the blue field lines coming from the pole. They actually connect from the northern hemisphere to the southern hemisphere. So the polar region is completely closed. And this is a closed magnetosphere. And another interesting thing is that the tail goes really long back. And they're connecting to this is because the boundary cuts off here, so they have to connect to it the IMF. But actually, the tail goes to the location of Saturn. This is what the bizarre Jovian magnetosphere is. So ever since we presented this field topology, there will be quite a few evidence that people are trying to show whether this topology is real or not. This is one of the best examples that we can get, is they're trying to look at the plasma property right near Jupiter, near the pole, and also the plasma property in 100 RJ, 100 UV radii in the tail. And you can see that they have similar ion dispersion. What's more important is that you see the oxygen ions and sulfur ions in the same distribution at 6 RJ and 110 RJ. So suggesting these two locations have the same plasma population. And that's a good indication that they might be close. They might be coming from the same flux too. If it's open to the solar wind, then you will expect here to see the solar wind population. Right? So this is Jamie Soleil's work in GRL. And also, we look at the convection pattern from the Juno simulation. That if you look at the Gamera simulation, you can see that this is red is co-rotating, and very dark is either rotating in the other direction or not co-rotating. So this is what you see in the observed azimuthal velocity from the Juno data. So this is quite consistent with what we see here. So we have co-rotating and connect to the solar wind, and the polar region is also co-rotating. So this is one of the interesting findings, and this is the published in Age Advances. So also because the topology is so bizarre, and the Jovian magnetopulsar connection is also very different. So if you look at the terrestrial magnetopulsar connection driven by INFBY, you have the off-site connection points, the anti-parallel locations in the dawn disk, and those symmetric. But if you look at the Jovian problem, you have most of the reconnection in the high altitude region, and also more on this side. And what's more interesting is that if you compare the cusp. So in the Jovian magnetosphere, the cusp, this is the prediction from the model results, that the cusp are on the dusk side. So all the cusp signatures on the dusk side. And this is also verified by this paper published in Nature Com, and to show that the cusp of the Jovian magnetosphere can extend to the night side. So this is because you have the rotation, you have the reconnection here, and then the magnetosphere rotates to the other side. And because it's giant, so the rotation slows everything down. And also the magnetotail is also different, and this is because of the rotation. And this is the observed X line in the tail, which has a very strong dawn-dusk asymmetry. This is looking down the equatorial plane. The Jovian magnetosphere rotates this way, bow shock. And this is a paper that JJ published last year, and this is the theoretical imagination picture published by Peter 10 years ago. And without global simulation, they were able to picture this, which looks exactly the same as the simulation, which is great. Right? So this asymmetry in the magnetotail connection is mostly due to the connection, rotation as well. The field gets really stressed in this direction, and then we get the reconnection on this side. But this is the one that I'm not talking about. The most interesting part that I'm really interested in is the internal dynamics. So this is another comparison of the simulation and the data is that these are the Juno orbits that's observed. You can ignore the details. So the blue bar plots are the data points. So this is a variation of density along the trajectory of Juno. So all the variations of the density. So the blue one is the observation, and the red one is what the simulation shows. So you can see that the density variation can be as large as 100%, which means that as Juno traversed the magnetosphere, the density of Jupiter is always doing this, right? So there are multiple ways. One, we have the structures over there. The other ones, you have azimuthal structures rotating. Because Juno is very slow, Jupiter rotates every 10 hours. So you see these structures going on. And the simulation did a really well job on this. And if Peter, this is a paper from Peter's student, and he originally used a quad-res simulation, and the two lines were exactly on top of each other. And then we said that's not good, because the referee will simply cherry-pick the data. So we used a higher resolution simulation. They're slightly off. But
is it known whether the Jovian magnetodisk kind of flops up and down like the magnetotail of Earth?
Yeah, it's every 10 hours. They have a 10-degree tilt. So the centrifugal equator, the current sheet flops like this.
Mhm.
So when Juno's staying here, and the current sheet goes up and down, up and down.
Right.
Sometimes across the current sheet, you have lots of variation
Yeah.
in density.
Okay.
But the problem is that these structures rotates, this will be every 30, 40 minutes. And the time that Juno's spending inside the current sheet is like 30 minutes.
Mhm.
So there's the strongest spatial temporal mixing
Yeah.
from one satellite. So it's not to say that it's a totally spatial structure.
So
Yeah.
you said when you use high resolution, you say data model difference.
Yeah.
But with the low resolution, you don't.
Yeah.
Why the high resolution make it worse?
Well, so the high resolution shows more variation.
Mhm.
It's because the high resolution code can handle more density gradient. So you can have more variations. But the low resolution seems to have the same kind of interval of the instrument, or the averaging interval of the instrument. So gave exactly the same profile. So we decided to use the high resolution bit. And high resolution is always better.
Okay.
Yeah.
So the data almost look like it's a bit like a bimodal, right?
Yeah, it's hard to say. Maybe two, yeah. But 50%, mostly it's 0.
But you don't see any evidence of that in your simulations.
Simulation, no.
Yes, okay.
No.
Just
And
good.
there's a big difference here, maybe related to the results, is that the magneto, the Jovian tail actually wobbles like this.
Oh.
We have a tilt, but in the simulation, there's no tilt, it's axisymmetric. So maybe, sampling the different size of the different way, inbound and outbound, you get different density. So to study this, I started the Jupiter simulation with MFLFM. And the reason I started MFL was Yuhong reminded me that at that old time, each year we had a computing quota, right? When it's used up, and you go on standby queue, it's free. Right, so I put on a high Octa as a MFLFM simulation because we were testing the outflow simulations for MFLFM, and I just increased the size, increased the rotation, put the outflow to be the equatorial outflow to mimic the plasma torus, and this paper is eventually published by John this year, which is great, which is like 15 years delay, but it's done eventually. So actually, what we found is that for the multi-fluid equations, what you needed, because you need the outflow flowing along the field line, so the parallel direction matters. But in the Jovian problem, we found this later, is that because it rotates so fast, most of the things are confined in the centrifugal equator or the current sheet. So it's mostly perpendicular dynamics. So single fluid did a pretty good job compared to the multi-fluid. So we switched to single fluid in the later runs. So it's mass conservation, momentum conservation, energy conservation, and magnetic flux conservation. So talking about this, since I taught MHD class last semester, which was pretty fun. It was based on Bill's lectures, but I removed most of the math. So, so always talking about the validity of MHD at different regions, right? So Earth, I know you guys are struggling in the problem with the inner magnetosphere when the drift kinetics is important, right? So in this plot, you show that different regions of peak or kinetic and hybrids, and also MHD validity with the two parameters, which is one is the gyro radius. No, this is GI, which is the ion inertial length divided by the planetary size divided by the ion inertial length. This is the gyro radius. So these are if we're doing most of the moons or Ganymede or Mercury and others, and you should use either hybrids or kinetic simulations. So on that side, then MHD is good, and Earth will populate different regions depending on whether you're looking at the outer magnetosphere, inner magnetosphere, or further in. But where is Jupiter? It's here. Right, so it's fantastic. It's probably over outside this room somewhere, right? Because Jovian planet's radii is 70,000 kilometers, and the magnetic field is 20 times more larger than the Earth. So the gyro radius is even smaller. So it's probably way out. So Jupiter is probably the best to test the bed for MHD, and most of the dynamics is perpendicular. Right, parallel direction we say MHD sucks, but perpendicular direction is great. Right, so that's why I like to move to Jupiter. Right. So this is what we did. That's the classic LFM grid to start with. We increased the LFM grid to be adapt to the Jovian problem. We up to res, so the highest resolution you can do is about 0.2 RJ in the inner region. That's close to the quad res that we do to the Earth. And then we add upstream solar wind. And for Jupiter problem, it's nice because I don't need to do storms like you guys do, because it's a Parker spiral and the IMF is a dominated BY. And you can calculate the flux to the Jupiter, which is 5 AU. Magnetic field is 0.5 BY, which is very steady. So nice, don't need to consider that. And mass loading is from the volcanic Io. Actually, it's not from the volcanoes directly. What happens there is that Io is very close to Jupiter 6RJ, so you have this tidal heating to causing the surface to be very unstable. You're kind of like squeezing the moon all the time. So you have 400 active volcanoes. And those volcanoes dump tons of mass every second to the space. Once they get into space, they form a neutral cloud, moving in the Keplerian speed. So you have a cloud of neutrals over there. And when the magnetosphere rotates, either through charge exchange or electron impact collisions, these neutrons get ionized. So that ionization rate is also very steady. It's about 500 to 1,000 kilograms per second. So this is also a fixed parameter. Rotation, 10 hours, that's also fixed. Gravity, also fixed. And my trampoline, it doesn't do much, but we can talk about this later. So for the Jovian problem, there's not much to tune. It's just a rotating, rotating plasma with a mass source, right? So this is what we did initially. And also you add the plasma torus right here, and you can see that the solver does a pretty good job on adding the mass to the system. And this is just a cut to the 5-6 in the inner boundary, showing you that we have a mass loading added to the inner region and it diffuses out slowly. All right, so this is the dynamics about the Jupiter. And then you look at the one on the left, everybody, most of you are probably very familiar. This is the high-res Gamera simulation of the Earth magnetosphere. This is one of the stuff that we did earlier. You can see that solar wind comes in, have the boundary layer dynamics, and the magnetotail starts, and the inner magnetosphere does not rotate very fast. And then you start to have the tail reconnection, bringing all those plasma, magnetic flux into the inner region and energize the ring current, etc. So it's all driven, mostly driven from outside. Of course, the internal dynamics is there. But the Jovian problem is completely different. You can see the difference between here is that you have these plasma mass loaded, and because they're rotating so fast, so you have the radio transporting them out. Once they get out, you start to see these structures and moving out, and these will come up with very large radio dynamic pressure and impact to the magnetopulse locations. So even under steady state, it's not a steady magnetopulse like this one. Right. Also, you have the magnetotail connection, some day-side connections as well. This is also found in the Galileo data. Juno is on the other side yet. So Juno is not here yet, and Juno is going to the southern hemisphere. So Juno hasn't been found this day-side connection yet, but we found the evidence in the Galileo data. Right. So internal dynamics, and you can see that the Jovian magnetosphere is mostly driven by internal dynamics. And of course, we always like to compare with the simulation with the observations, right? So this is the red one is the simulation average, and this is density, and the others measurements. This is the pressure, this is temperature. So they look more or less okay, but there's a problem here. It's inside 10 RJ, there's a big difference. And I'll come back to this and why this is important. Looks like we're doing a good job, but it's actually not. So I'll come back to this later. So one of the interesting findings that we found that internal dynamics is important is that the magnetopulse is not steady. So this is an in-house paper published a while ago. It's showing that, so if just for the pressure balance, you have the solar wind dynamic pressure. Solar wind dynamic pressure balanced by the magnetic pressure of the magnetic field, the magnetopulse should be at 42 RJ. But what's observed is from 60 to 90. And we always contribute this to the thermal pressure of the plasma, which has a beta larger than 10 outside. But it turns out that if you're including the radiodynamic pressure from the disk of those structures, then you can get a magnetopulse location around 70. And this is exactly what's happened in the observation. And what's interesting, I just had a conversation with Peter a few days ago. He said that after a few of these years of the Juno's observation, they have 16,000 magnetopulse crossings. You know, Juno orbits every 53 days. Every time they got this, they got thousands of magnetopulse crossings, saying the boundary is probably doing that, right? And the reason why the boundary is doing that is probably because, look at, this is the radiodynamic pressure, and the solar wind dynamic pressure is quite fixed in time because it's a constant driving. But the structures coming out through the radial transport here, as you can see, the dynamic pressure can dominate all the terms. And that's why you get the variation of the magnetopulse. And you will see these dayside reconnection through the stretching of the flux tubes and the interchange structures, and also density variation. This is Peter's paper that's JJ published this, and also the magnetosheath periodicity. This is also consistent with what's observed in the magnetosheaths. So more or less, this is doing a pretty good job simulating the structures. Now here comes the question, right? So if you look at this, the conclusion is that the rotating magnetosphere, like a Jovian magnetosphere, is never steady. So what happens if you look at the force operator? But this is a linear. So you have waves. Let's ignore these are boring. So what's important is that it's always a balance between the pressure gradient force and gravitational force and centrifugal force moving out, and also the magnetic tension force. So when including these terms, and you can in the simulation, these three terms never balance. So that's why you get all these structures generating out. If you move the background, and you can see that in these regions, we call these finger regions, you can see plasma moving in and out. So this is kind of like the interchanging motion that you're talking about. So this looks great, and we did a lot more detailed analysis on the force balance problem here. And this is a three-dimensional picture. So I showed these some of these results at the MOP conference last year, and it was great. Of course, I think it was great. But except
Magnetospheres of outer planets.
yeah, so Fran asked me a question, and she said, "You know, these are beautiful simulations. These are beautiful simulations, but we don't see these in the data." What shall I say?
Data is not right.
Well, I kind of said that's not my problem because I don't look at the data. So here's the story. First half of the story is that from the global simulations, we know that you have these structures, right? Now the question is, conclusion from that is the Jovian magnetosphere is interchange unstable, and then we're done. So we can go back to work. Colquhoun is done.
But we're not done.
Is that true? Are we done? Of course not.
Go ahead, Phil.
All right, still have 20 minutes to show. So I have that's the second half, right? So now here's the problem, right? Yeah, the problem comes from exactly from where we have. So look at this. Everything I did in the MHD simulation, that it's an adiabatic fluid, right? It's an adiabatic ideal MHD fluid. But if you look at the Jovian profile of the plasma pressure, and you will see that this green line is the thermal plasma, in which the code does a reasonable job on modeling this gradient. But there's another important factor, important species, the energetic ions. So these are the non-thermal population, and they're actually much harder than the thermal population outside 6 or 10. So this part is how these energetic ions are heated, and we don't know we know that yet. It's probably kinetic. I think the heating of this is either kinetic or through turbulence, and this is also something that we don't know yet. It's similar to the corona heating problem. It's just very hot. Look at the ratio between hot and cold. It's about 10. So the pressure is dominated by the hot population, which was not included, which means that the MHD pressure profile that you get, MHD pressure profile you get cannot support this kind of density gradient. It only supports this one. So that's why the difference here is important. So we don't have these enhanced plasma pressure, because from the physics that you have the enhanced plasma pressure gradient that stabilizes the system, right? So the physics is here, right? So if you just look at the incompressible fluid, as long as you have a density gradient against the effect of gravity, it's unstable, right? It's incompressible fluid, that's very simple. But for the magnetosphere, it's not, right? So the magnetosphere, that you have to consider the specific entropy, which is a combination of pressure and density. So this one is determined by the rate of changing the pressure and the density, right? So simply, what happens in the physical picture happens if you have a plasma and you have an interchange motion, so effective gravity pointing radial outward, right? So if you have a switch in the plasma, and you release the potential energy, right? So where did the energy go? If it's incompressible, it all goes to kinetic energy, and it's unstable. But if it's compressible with the specific entropy, depending on what the pressure profile is or temperature profile is, the energy can go to thermal energy, right? So after the interchange, if the energy all goes to thermal energy, it's stabilized, right? Which is an effect that the ideal image theory does not capture this fact, right? So that's why with this picture, we don't really know whether this is stable or not. So I thought about this question, and I think, then the first thing came up to me is that we need to look at the equations to see if we can derive these from a theoretical perspective. So I went and talked to Bill last year. It was about the same time earlier. And then we talked along for lots of stuff, and he eventually memorized that he had wrote a paper 30 years ago on this, and he and dig it out on your bookshelf, and then started to this dipole geometry and linearize the MHD equations of this dipole geometry. But this paper was for the waves with the transporter wave energies, not interchange stability. But the idea is very neat. So you start with the linearized MHD equations, and you do some math with the normal mode analysis. You do the Fourier transform and look at the three directions. One is the azimuthal Q. Two is perpendicular to the field line, and the three is along the field line. So you do this kind of analysis, you get reduce the equation down to a linear system with all these A1, A2 coefficients, and eventually came up with a frequency called, which is similar to this Brown. I don't know how to pronounce it, but Vaisala frequency from the hydrodynamics. So it's basically buoyancy. And this nice thing about this equation is that you can eventually reduce the equations down to criteria like kappa C, kappa B, and kappa P. Here are the definitions. They have very clear physical definitions. Kappa B is the radial gradient of the magnetic intensity. So that's the gradient of the B field. P is the radial gradient of the plasma pressure. And C is the geometry curvature of the field. So it's basically a computation of the pressure gradient and the tension force, right? So this is a very clear physical picture of how to analyze this. So based on this idea, so we think that, oh, it's easy. We just add the effective gravity and rotation in this equation, and we can derive something similar. And we know we can prove whether it's stable or non-stable, right? So we did this, right? And this is why you need good graduate students, right? So, because we were not able to reproduce that results last year. So started talking with the graduate students. So here's what we did. We started with the MHD equations, and it was easier to do it in the rotating frame. So you just added gravity, Coriolis, and the Coriolis force, and the centrifugal force. So adiabatic equation and the Faraday's law. So the hope is that, so the only difference with this and Bill's technique is that you didn't have this term, right? So adding this term sounds like a very simple task to do, but MHD equations are not. MHD equations are helpful, right? So we were hoping to derive these equations with A1, these parameters with the rotation and the radius in it, and so we get a better, theoretical description. And that's the results. Right, so that's a A11, A12, A21, A22. They look like something, right? You do have something. You have the density gradients, you have the pressure gradients, you have the magnetic field gradients, and you also have the gradient curvature, all these crazily combined terms. So adding one term to the linear equation ended up with completely crazy results of the analysis. And then we look at this for a long time, and the conclusion is your MHD exam is failed. So that doesn't give much information, right? So that's the interesting part of working with good graduate students, is that you need to do a reasonable amount of assumptions, right? Especially with algebra work. So, for example, if you apply these like a Bose-Nassic approximation, the subsonic rotates very slower than the alpha speed, the sound speed, and the low beta and other field assumptions, you can actually reduce the frequency down to this thing called the Rayleigh-Taylor frequency, right? So it has three terms. One is the density, one is the pressure, one is the magnetic field. So this is good enough to tell whether it's stable or not. So the density gradient term, because there's a negative sign, and as long as the density drops outward, it's always unstable, which means that you have a density against the change of the potential energy. And the pressure term is interesting. This is positive, right? So which means that the pressure term always stabilizes things. So this is why this is what makes me worry about the global simulations that we get, is because the pressure profile or the pressure gradient that we model in this code is not correct yet, right? So this term stabilizes the system. And then the third term is also more complicated because depending on the gravity and also the beta and also the variations in the magnetic field with the grid variation, and this term can go either way. So the magnetic field can stabilize the situation or destabilize it, depending on what configurations you're in. So, but with this one, in general, like if given the rho P and B, and you can plug in to these numbers into that and can work out whether the magnetic field is stable or unstable. So this gives you some idea whether it's stable or unstable. I can tell you that if I plug in the profiles from Fran's paper, it's unstable. So that's great, right? But this is still too complicated. So we continue looking for a more even, more physically illustrative way to answer the question. So, yeah. So eventually came back to this analysis. So the idea to analyze this is that, for example, like the Rayleigh-Taylor spread F instabilities, that if you have perturbation, it's going to generate these secondary electric fields. If these electric fields further accelerates the plasma, and then it's unstable. If they suppress the variation, they don't, right? So you can use this kind of method to analyze a rotating plasma, like the fluid instability, which is basically the fluid instability, and it's from Chen's paper. And what we found is that also from Bill's office, it's a very old textbook written by George Siskel, and the calculation is already there. So it's done before I was born. Right? So here, this is a very elegant way of looking at this problem. So if you look at two situations, this is the equilibrium. You have two fluid parcels, 1 and 2, and they exchange location. And then because of the shift, and they also move in this direction because of the gradient here. So this is exchange equilibrium position and interchange position. So a couple of assumptions: pure dipole, no tilt, and the kinetic energy of plasma is much smaller compared to the magnetic energy. Also, thermal energy is small, so it's low beta plasma, which means that during the interchange, the magnetic energy is not affected. So it's just the magnetic fields are applying as containers of these plasma. They just change location, right? So we don't need to consider the influence of the magnetic energy. So what happens here is the idea. So the basic idea comes with this way. So we have a perturbation here. So after the exchanges, there is a gradient in the azimuthal direction, right? So it's just like the Rayleigh-Taylor analysis. You have gradients, and this gradient will generate a current goes through the ionosphere and generate an electric field, which is going on this way. If this electric field push the plasma parcel out, it's unstable. If it pushes in, it's stabilized, right? So this is the idea how you work with. So start with the momentum equation. Now you don't need to go to normal mode analysis, and you don't need a good graduate student. Even I can understand this. So you start with the momentum equation. We say this equilibrium and slow flow. I'm acting like I'm RCM, but it's not RCM. So you end up with a pressure balance, force balance between the J cross V force and the gravitational and the grad P force down here. So the perpendicular current is calculated as B cross grad P minus rho G star. G star is the effective gravity through rotation. Right. So So this equation says that the current flows perpendicular to the magnetic field. This is the current that keeps the whole thing in equilibrium state. Right. So now you can link the perpendicular current with the azimuthal electric field to determine whether the situation is stable or not, like the same idea. So this is a very neat idea. So in the ionosphere spread F, because it's collisional, and then you have perturbations that you can, due to the motions, and you generate these electric fields. And they push the ionosphere up to amplify these perturbations, right? So in the collisionless plasma, there's no charge separation beyond the device scale. So this is the reason why I have lots of problems with pictures like that. Although I think the process is correct, but this kind of charge separation is not acceptable because it's collisionless out here. So if it's collisionless, where do we have this charge separation for the electric field? So what generates here is that you have a displacement in the azimuthal direction, you generate a perpendicular discontinuity in perpendicular currents. But these field lines are connected to the ionosphere. So the currents are closing through the ionosphere. And depending on the gradient of the currents, you have the electric field either pointing this way or pointing that way, or azimuthal direction, pointing this way or that way, and then map to the ionosphere to decide whether it's stable or unstable.
I thought you said magnetosphere coupling was not important.
2-0 further. This is high order. This is perturbations. Okay, I should be more careful about it. The reason I said it's important is because I don't want to do it.
And furthermore, collisions are important down in the ionosphere, right?
Yeah.
Sustaining that electric
Yeah,
field.
that's the collision sustaining electric field, not the charge separation.
Yeah.
Right. So now coming from this, right? So through the current closure, you can work out the variation of the parallel currents in the zeta. Let's work with the cylindrical geometry. Ignore alpha waves, so there's no gradient on the B. It's just no alpha waves. So it's just the variation of the P and rho G. This is basic. This equation is basically the gradient S dot G star. So what happens here is that you can work out the d by dz of the parallel currents, and this current determines the change of the currents along the z direction, and which determines the direction of the electric field in the ionosphere, whether it's this way or that way, because the current's closing through here. So eventually, after some math, I think this calculation is probably correct. So you can show that dj dz is equal to some equation like this, which is the azimuthal gradient of 3p plus gamma rho times g star. So this is current generated by a radial interchange of motions. So you have a gradient in this direction, and that gives you a current variation of the current down here. So this current eventually going to be closed through the ionosphere and decide whether there's E phi. So decide whether you have a positive E phi. If you have positive E phi, so E cross B. So B goes downward. So Jovian magnetic field going in the opposite direction of the Earth. So you have a positive E phi, and then you have unstable situation. You have negative E phi. You have stable situation. So eventually it becomes comparing whether this the sign of dj parallel dz. So comparing this to the unchanged situation. So come up with the idea. So I'm not going to talk too much on the details. So the idea is that you just compare the exchanged value with the adiabatic value, which is the environment, the background value with the exchanged value. So this equation is very handy because you can reduce it down to something like this. If you assume the adiabatic value is PV to the gamma, and then you can get to the on the left-hand side, right-hand side. On the left-hand side, it's based on observations. So you have two parameters. One is the density profile. One is the pressure profile to the power of density to the power of mu, and pressure to the power of lambda. So mu in Jupiter around here is about -8, and pressure is about -4 in this region. So you can plug in numbers into that equation, and eventually it becomes a criteria, something like this. Just put in lambda and mu, and plus the values of P, G, and R down here. So you can kind of see this, right? So if it's incompressible, pressure doesn't matter. This term is always negative because mu is -8. So it's always unstable, right? When you consider pressure profiles, so compressibility. So lambda, if lambda increases, and this is positive, right? It's gonna increase this term, and it's gonna stabilize this equation. To some extent, if lambda is positive, and this term can be larger than that, so it stabilizes it, right? So the stability criteria is determined by the pressure profile, which the global MHD code was not able to capture down here, right? So what I did is that I put Fran's profile into this equation, and they're all unstable. So that's nice. So I can answer her question that it's unstable based on your observations. Right? But still doesn't solve the question that how do we do this in the modeling side. So is it unstable? Do you guys believe it's unstable?
Well, you just showed it was using Fran's parameters.
Yeah, but that's Fran's parameters. And you said the observations are not correct, right?
Yeah.
So there are more interesting questions to look at, right? So what do we do, right? What do we do starting from here, right? So I had this discussion with Bill last year about creating this crazy model, solving the equations on the regional MHD grid. So it's a local dipole grid, and Jupiter's right here, put the Ion Taurus here, and let it rotate. So we can squeeze all the resolution into this small region for very fine grid and to study this. So this is a regional code that we do. So why we're moving to regional calculations, right? Theories are nice. They're physical, and math are very elegant, and they're very cheap. You just need a pen and paper to get to the derivations. But they only apply to simple geometry, and they usually work for linear regime, and you need good graduate students to do it, right? So we couldn't do it last time, right? And the global MHD, they're nice because you have the real configuration and the boundary conditions very physical inside and outside, and you have a nonlinear process included in. But the resolution is limited. For example, the one that I showed, the 0.2 RG, that's about the largest we can go. If you go further, you need to go hex, will be 0.1. Still 0.1 RG, not fine. It's very expensive. And only in ideal MHD, because if you want to include non-ideal MHD terms and the shocks and all other things are affected, and I don't deal with that. And another problem we found recently that the global code that we're using, that we have angular momentum not conserved. So this is also a problem that I haven't tested very carefully yet. So the regional one, there's non-ideal MHD. You can add Hongyang's double adiabatic MHD solver in it. We can add the heating functions into it without worrying about the shock. And we can go to very high resolution, and we have angular momentum conservation. This is all I care right now. And drawbacks, yeah, haven't found yet. So this is great. That's why I like regional simulations. All right. So what we did here is that it's a upgrade of the Cartesian Gamera solver. So we solve the equation on curvilinear orthogonal geometry. For example, this is the dipole geometry that you do with the Q, P, and S, a Q, P, and phi along the distance. And so the new solver, the original Gamera solves the equations on a X, Y, Z based, the Cartesian-based coordinates. So although the grid is a stretched spherical grid, but all the vectors are solved are the X, Y, Z. So it's just giving rotations to the interface and calculating normal phase, etc. But this new code, we want to conserve angular momentum, so we have to solve the equations in the linear geometry. So you're solving the equations, vector equations on P and Q and phi. And it uses a high order reconstruction method, which is based on the Berry center reconstruction rather than geometric center. And also use the enhanced PDM method, which is a paper just published. It's a Hongyang's paper on the making good convergence and monotonicity preserving for curvilinear geometries, and also used a very fine technique to conserve the angular momentum, which is very important. So if you look at the regional simulations, right, so this is a Tesla simulation. So it's a dipole grid. You're working on a dipole grid. It's orthogonal. So what we're going to do is we're going to initiate a high pressure in the middle and see the blast wave. So you can see that the blast wave simulation, you can see that the wave, the solver captures the blast wave to a pretty good resolution. The solution is not determined by the grid, and it's pretty circular. And this is solved on the dipole grid, and this is test simulation. It heritage of the Gamera's high order reconstruction, but the fields are now orthogonal and now with angular momentum conservation.
I mean,
So,
sorry, is the grid then similar to like a SEMI-3 model? Of course, the SEMI-3 is not an MHD, but just like the grid, is that like, do you consider like SEMI-3 a regional like this?
SEMI-3 does not, SEMI-3 solve along the field lines, right? So it does not require cross the equations along the field lines.
Okay.
So it doesn't matter. I don't think it matters.
Okay, but I was
Perpendicular direction is just the same. So it's not the same. This is orthogonal. SEMI-3 is not orthogonal. I don't think it's orthogonal. Anyone can correct me.
I was just looking at the grid, kind of the general grid configuration. I mean,
Yeah,
so there's a donut shaped structure. Is that, in that sense, is that similar to?
it is similar, but we are more strict with solving the orthogonal
Okay.
part.
Sammy's kind of orthogonal or dipole-like, but because the low altitude boundary is spherical, that's not a coordinate surface.
Oh,
Mhm.
okay.
And so it's not fully orthogonal.
Yeah, it's not fully orthogonal, and mostly semis along the field line.
And it's only solving, it's the solver for parallel transfer.
So the field lines can have different field lines. And this is just solving the MHD equations. So we solving the MHD equations, mass, momentum, and energy, Faraday's law, Ohm's law on that grid. So to make life easier, we just solving in the table frame. So you just add the Coriolis and the effective gravity in the momentum equation and the energy equation. So these are source terms we added. And then we have model the region from 5 RJ to 25 RJ and azimuthal direction. Assume it's periodic in the azimuthal direction. So we cut a pi/3 region to do the simulation. So the regional grid can be down to 32 by 2556 and 128. And this have a delta R is 0.078 RJ. This is a very fine. This is not the finest resolution you get, but you can go down to 0.07. Right? And then the global resolution goes to 0.15. This is already the highest that we can do beyond that. So starting with the uniform magnetosphere, periodic boundary condition, and ionosphere, it is not important.
Yeah, your ionosphere is a
No, you know-
dipole surface, not a.
In the rotating frame, it's just a constantly rotating around. Yeah, we will do the ionosphere later, and I can show you that the field line currents are essentially zero. And the IO source, we put in a plasma mass loading down there. So this is what the student did, right? So eventually, before I play this is the simulation. After initially you have these interchange structures coming out, you have about 24 fingers, which is quite close to what the global code has, right? 24 fingers, you have about 1, 2, 3, 4, 5, 6 in each quadrant. So about the same. So which means that in terms of grid resolution, the global code is probably okay. It's already started to converge to something. While the dipole code. So this is a simulation from the dipole grid, and this is the dipole grid in this way. So we're looking at the equatorial plane, dipole goes that way. So this is the equatorial cut. So if you run this simulation, you have starting from an empty magnetosphere, you add the plasma mass loading down here, and then initially you see these fingers coming out, but they quickly mix in the azimuthal direction. And because when they go out and the angular momentum has to be conserved, so they move in this direction very quickly, and they get mixed. And eventually you start to have structures. This is a log scale, but if you look at the linear scale, you clearly see structures here around outside 10. Lots of structures outside 10. So let me do it again. And initially, this is important. You see these structures initially because you keep adding the mass load. This is related to the way that we add mass loadings. We only add the region in the torus. So the density gradient becomes extremely large.
Mhm.
Right? Extremely large, you know from the theory that large density gradient becomes very unstable. So initially it's unstable everywhere. But then once they come out and they move further out, then the angular momentum is conserved. They have to mix in this direction. So eventually they become more or less mixed and can come into a situation what's going on, some situation like this. So what happens in this code is that inside the 10, maybe 12-ish, what we got is marginal stability. So it's that the equation from the Cisco's paper to equal to 0. So you get a density pressure profile following that equation. Further out, the magnetic field beta increases, and the magnetic field becomes less rigid, and you start to see structures further out. And we haven't done a very careful comparison yet. This is very preliminary results, but according to Peter, and this is what they found in the data. So most of the events of the interchange events were found outside 10. So most of the structure they found outside 10 RJ, and this is what we show here. So there's a difference between this one. So here in the global simulation, you do have these structures starting from the torus. And this is possibly related to the reason that the angular momentum is not strictly conserved. It's not too bad, but with the truncation error, because the angular momentum is a expansion of the stress, and then when you move out, you always have a truncation error to the delta x to the second, the delta v to the 2. So you have this. So the difference between these two are very interesting, and this is what we're gonna figure out in the future. We're gonna run this to a higher resolution and the better boundary conditions and better mass loadings and others to figure out what's going on. So here comes the issue again, right? So outside 10 RJ, you can see this is radial distance 10 RJ, and this is density profile. You can see that outside 10 RJ, the code is doing pretty much good job compared to the observations. And this is also what the global code can do. So the global code does a very good job on the density profile here. So inside 10 RJ, that's the problem. This is the marginal stability profile that we get from ideal MHD. So the hope is that if you want to make it more stable or more unstable or whatever inside this region, is that you need the non-ideal terms. For example, heating the plasma. If you heat the plasma, have a much more steeper pressure gradient, and you can have a density gradient into much higher. You can level up the marginal density gradient down here. So this is exactly here right now, because our lambda is the adiabatic pressure gradient that we can have. So mu is about -6. If we do this to whatever observed, and then mu can be -8, which is closer to observation. If we believe observation, shall we? Okay. So this is a nice part of doing work on a regional code, is that we can add non-ideal source terms to the energy equation. We can also apply the double adiabatic equation with the anisotropic pressure, and to study different things, and without worrying about the shock and other problems. And you can go to very high resolution. All right, so a quick summary. So I think rotating magnetospheres behave fundamentally different from the terrestrial magnetosphere, and it's mostly internal driven. Dynamics are most from internal. And interchange is one of the key questions in rotating magnetosphere. The problem is that we don't even know whether it's stable or not. From simulations, it's not. According to the friend, they don't see those structures. But from the theory, it should be unstable. Right. So now how do we resolve that question? So it should start from both data and the model. So combined with the observation profiles, MHD theory says it's unstable in most of the regions due to it's just the partition of the energy. But pressure is the important thing. So pressure profile, which means the energy equation dominates. So we need better energy equation based on the measurements on how the plasma heated up. But that could be those. I think not could be. Those are kinetic processes. So we may need to go down to kinetic simulation to see what's going on there. And global simulations are great, but they have problems for rotating magnetospheres. The grid resolution is probably not good enough, and it's hard to implement non-ideal terms, etc. So that's why we move on to the regional simulations, and hopefully we'll have more work by incorporating non-ideal terms, and this can also be used to study turbulence eventually, because turbulence is the end of the study, right? Once a field moving to turbulence means that it's ended. Right?
That's right.
Okay, so this is all I have. Thank you.
Okay. Questions? Yeah.
So I believe that your dipole coordinates are much better, and that this code conserves angular momentum. And what I haven't wrapped my head around is why the Gamera grid doesn't conserve angular momentum.
Oh, okay. So this is a figure that I think Hongyan did a while ago. I can show this easily. So if we have a grid domain like this, and we only conserve the linear momentum x, y, z, right?
Yeah.
So for example, if you apply stresses across the boundaries like this,
Yes.
right? So these will be canceled out. It's exactly zero. Linear momentum is exactly zero. It just cancel out.
Yes. Yes.
But you're creating angular momentum.
Yes. Okay. Good picture.
So if you have cells
Yeah.
moving in this direction, but your vector is XYZ, any ripples going through these cells will be creating this. So it's possible that when these structures going out, it's creating angular momentum on the way. So it's much easier to transport further out. You see the dipole coda, they curve or mix very quickly in the azimuthal
Yeah.
direction.
Yeah. Yeah.
If the implementation is correct,
Yeah.
which I think that we should believe graduate students, right?
Good. Thank you. Dr. Lentz.
More?
How regional is your new regional model? I was wondering if you can do plasma simulation inside this.
For Jupiter, we do now. It's flexible, but for the tested case, I showed it's from 5 RJ to 25 RJ, 5 to 25.
Well, I don't have a number on my head. Is that the possible range that we can do plasma simulation?
What do you mean plasma simulation?
Maybe particle simulation.
Oh, particle simulations. Why do you want to do particle simulations?
You say that here there are still something that cannot be described by
Oh,
the
oh yes, I
Right.
get your point. So yes. So my understanding is that if I want to embed some kinetic or particle simulations,
Mhm.
the scale will be too small.
Oh,
Because remember that in MHD picture that Jupiter is way over there, kinetic scale down here. So kinetic scales, what we do is we're gonna pick a few points, pick the local parameters there and do local kinetic simulations there and get some parameters.
so
Rather than do it globally.
this is
because
too large.
Yeah, scale separation is too large. There's no point to put them together.
So how do you specify the boundary condition for your regional models?
Okay, so because it's in the reason why we stop at 20-ish RJ is that inside 2030, the whole thing assumption is that whole thing co-rotates.
Okay.
So we just specify co-rotating velocity for the outer boundary, and in the inner boundary, it's also co-rotating. And because assumption is that field line currents, well, it's true, field line currents are small, so we should assume that there's nothing going on. It's in a rotating frame, so it's in a rotating frame, so that you just fix the electric field here. There are current closures, but they close wherever they want.
I have a question on your conclusions slide, the third point. I think, if I understood right, you were saying that the observations suggested that it was not unstable, but the theory suggests it is unstable. And so, but it's often the case that the observed profiles, the mixing has already occurred, the instability has already happened. The system is at marginal stability or something like that.
Yeah.
Is that?
So, well, first of all, the observations I mentioned, that's Fran's imagination.
Yeah.
She thinks that there's no structure. But right after my talk, her former student, everyone came to talk to me that they think it's structure. Including the guy who just defended it yesterday. He showed me these radial velocities during Juno crossings, like in and out. So they think it's this. So what I think she's saying is that so the conclusion based on the observations that if I take these profiles, put into the theory that's derived, it's unstable. But according to her interpretation, there are no structures. And her students said something else. So there are lots to do in the. But you're right. I think what we're getting, if the profiles, these are data, right? And this is also measurements. So if these are correct, means that these are marginal stability profiles. But the MHD simulation definitely cannot get there. It's not there yet. And then the problem is in the energy equation. So we don't have a good energy equation at the moment. We need the observations to tell us what to do. Not tell us it's smooth, but that doesn't help.
So what kind of observation or you send more satellites to there to measure to uniquely determine some stable, unstable?
It's not easy. So especially the inner regions, right? So there are only very few data points because its radiation is too strong. So the radiation marriage is left to show like this. So they're all energetic protons and electrons in. So all the orbiters inside, even including the Europa Clipper, which is orbiting, it's a Jupiter orbiter. So it orbits Jupiter every time going through pass by Europa. Because you cannot send this to 10 RG to do the orbiting because its radiation is too strong. Satellites will be destroyed after a few hours. So that's why collecting data is very difficult. And another trick is that the system wobbles around. So current sheet, there's 10 degrees tilt, and then the current sheet wobbles around very fast. So every time you go through, you only have a very limited time to go through the current sheet. And it's not very easy. And China is going to send a satellite spacecraft to Jupiter, which is called the Tianwen-4 mission. It's going to be orbiting Callisto, which will be somewhere here. So one thing we're proposing is that if we see these structures, right? So at the location of Callisto, we should be able to see all these modulations in the field, in the velocity density. So that would be a good verification because Callisto stays in the current sheet for a long time. And if you have the orbiter there. But the bad news is that that mission will be heavily on geology. So they're gonna spend more than 90% of resource for a rover land on Callisto. Although I don't know why we need to land on Callisto. But geology dominates the planetary science. Right now, our planetary science is mostly planetary geology. But anyway, that's a different question. But the hope is that we will have more data at different places. And JUICE will also do something similar. That's the ESA's JUICE mission. They'll be orbiting Ganymede around somewhere here.
Okay.
Well, before we let Ben leave to retrieve his kid from camp, are there any questions online? And any of there are several people online I see, but who aren't in this room. No questions online?
I have a question, but I can ask if it's too late. I will ask later.
No, it's not.
At the end, you said, maybe not the very end, but you said if it's non-ideal MHD, there's a problem in the global because if I understand correctly, you said may cause shocks, things like that. But why? Maybe first, why is not a problem for regional model, or is it a problem for regional?
For the global simulations, right? So the issue is that you need to handle shock problems and magnetic connection somewhere, and also telluric connection and others. So if you're adding all these, if you're modifying the energy equation, energy is no longer conserved, and then your shock location, shock speed will be wrong. So if we don't have a correct shock location, and what kind of Magnetosphere you're simulating. So that's one thing. The other one is that if you try to apply the double adiabatic pressure anisotropic solving, and then that's related to the relaxation time because the fluid anisotropy theory only describes one type of instability other than kinetic, like a mirror and iron cyclotron with kinetic instabilities. So you need to put in a relaxation time to isotropize your plasma. So if you're doing this on the global scale, what time scale do we use? Inside a little donut, it's a lot easy to choose and experiment. So that's why trying to avoid the trouble for going further out. And also just assume everything co-rotates, and it's also a lot easier for the boundary condition.
So for the little donut simulation, regional simulation, you don't care about shocks because there are no
There are no
shocks.
shocks. It's so we only look at this 20. This is Callisto orbit. So we're simulating this little region and it co-rotates with the planet. And it's not a bad assumption that it co-rotates because it's so close by.
Okay, well, let's thank Ben again.